Hey everyone, welcome back to another video of Cam Room 5. We're going to continue with the idea of separation techniques, building up on the concepts of mixtures. The first technique is filtration. Now what is filtration? Filtration is done to remove the undissolved, or you can say insoluble, solid particles from a solid liquid mixture. Now we should remember it wasn't a solution, it was rather a suspension because it was not uniform. The solid particles were not soluble in the liquid. We separate the solids actually on the basis of the particle size, because the solid particles which are insoluble cluster together to make large sized particles. So imagine you have a test tube which contains like insoluble precipitates, for example calcium sulfate or barium sulfate, and the water was still there. So you pass it through a filter paper which has a very specific pore size which is set on a filter funnel. The filter paper is folded in the form of a cone, and when the test tube containing the mixture is poured onto the filter paper allows only the liquid portion to pass through. The solid is going to stay on the filter paper, while the liquids along with the dissolved substances definitely pass through. So the undissolved substances are called the residue, which remain on the top of the filter paper, and the liquid portion along with, like you can say, solvent, water, dissolved ions, they're called the filtrate, which are passed through. Now I'm not saying that it is pure water, it can have dissolved substances, but at least the indissolved substances or the insoluble substances are still on the top of the filter paper. So you need a filter paper for the process. Once the filtration is done, you make sure that the residues, if you need the residue to be pure, you just wash the residues with distilled water, with cold distilled water, because if you want a pure residue, for example if you want pure precipitates of barium sulfate or calcium sulfate, you wash them with cold distilled water. So if there's any other kind of filtrate remaining on the residue, it passes through, and then when the residue is washed, you dry it using filter paper. Another process is called crystallization. As the name suggests, it is used to obtain pure crystals. We are concerned with soluble salt solutions, or you can say solutions of soluble substances in general. So here we talk about obtaining pure salt from aqueous solution, or you can say any kind of solution. It could be a solution where the solvent is organic in nature, it's not water, it's some other kind of solvent, but at the end of the day the solid was dissolved in the solvent. You need a china dish where you add the solution and you strongly heat it. You heat it to a very specific point which is known as the saturation point, because when you heat the solution, some of the solution obviously vaporizes, some of the solvent obviously vaporizes, and it reaches a saturation point. A saturation point is a very specific point where the solution contains maximum amount of solute dissolved in it at a particular temperature. So it's a solution that contains the maximum amount of the solute that could be dissolved in it. No more solute can be dissolved in it right now, because it contains the maximum amount of solute dissolved at a particular temperature. So based on the temperature, it has the maximum amount of solute dissolved right now, and now if it is cooled, the solubility will decrease and the solute will start to make crystals. So what happens is, when you cool and allow the solution to evaporate, the solubility decreases and a lot of the crystals start appearing at the bottom of the beaker or the china dish. Now, some solution is still going to be there. How do you remove it? You filter it. You filter it very, very, very delicately so that the crystals remain on the top of the filter paper, and the remaining solution, very small amount of the solution which remained after the evaporation, passes through. You wash the crystals with organic solvent, because you don't want the crystals to dissolve again, obviously that's why you're not adding water. So you wash it with wash it with organic solvent, and then later you dry it using folds of filter paper. Filter paper over here is just working as a drying substance. You're just using it as paper towel, nothing else. You need to use the words of cool, evaporate, filter off the remaining crystals using organic solvent and then drying. With this, we are going to start a new separation technique which is called distillation. Now in distillation, what we do is we actually obtain pure solvent. In crystallization, we were obtaining the crystals of solute. Here we are obtaining the pure solvent. So it's a process where we separate the mixture or the components on the basis of the difference in their boiling points. Now it can be used for a solid liquid solution, or it can be used for a liquid solution as well. Now that is interesting. We can have two kinds of distillations. One is simple, the other is fractional. In simple distillation, we obtain the pure solvent from a solid liquid solution. It may be a solution of copper 2 sulfate in water. It may be a solution, for example, ink components dissolved in water. While in fractional distillation, we obtain a pure liquid from a mixture of liquids. A mixture of liquids can be, for example, water and ethanol. It can be a mixture of, for example, two different organic solvents like heptane and hexane, for example. Imagine you have a round bottom flask. You have an electrical heater at the bottom, you have a rubber bung at the top, and you have a thermometer at the top. There's a delivery tube coming out of the round bottom flask connected from the rubber bung. And then you have something interesting called the Liebig condenser. Imagine in the round bottom flask, we are calling it round bottom flask because it is round bottom, because it has a round bottom. So it has a solution of copper 2 sulfate. Remember, the 2 at the end of the copper indicates the oxidation state of copper. So it's copper 2 sulfate. And then you have an electrical heater. It could be a simple Bunsen burner, but generally we use electrical heater if it is flammable. It's not flammable, but still we are using electrical heater. When you heat it, the vapors are going to rise, the water is going to vaporize, and thermometer is going to check the reading of the temperature. It's going to tell the temperature of the vapors. The vapors, these are the vapors of the water, they're going to pass through the delivery tube and they're going to pass towards the conical flask, which is put at the end of the Liebig condenser. The Liebig condenser over here has two outlets, like an outlet and an inlet. Cold water is going to be allowed to pass from the inlet, which is at the bottom. From the inlet at the bottom, there's cold water coming in, and then cold water is filled in the entire Liebig condenser. So delivery tube and Liebig condensers, cold water, are very much in contact. They are not mixed, but they are in contact. So when the vapors are passing through the delivery tube, the cold water is being passed through to the Liebig condenser, and this allows the condensation of the vapors. So in the delivery tube, the vapors become condensed, they become liquid, and pure water is collected in the conical flask. So this is pure water. The copper sulfate solute did not vaporize. It did not pass through the Liebig condenser. It is not collected. It is pure water at the end of the conical flask. In the Liebig condenser, the vapors lose their heat. They become colder, they condense, and they become liquid. This is the process of simple distillation. Make sure that the water collected is really hot so you don't have a rubber bung on the conical flask. Otherwise, there's a chance of bursting.
If we have the school,
Fractional distillation also has a very similar setup. But what actually happens in fractional distillation, we are dealing with a solution which is two liquids over here, which is a simple solution again. Over here, there is something interesting on the top of the round bottom flask. Again, there's a thermometer, there's a delivery tube coming out of the round bottom flask. There is a conical flask at the end. A similar Liebig condenser has to be there. The electrical heater is there. Setup is very similar to simple distillation. But on the round bottom flask, there's something we want to talk about. And that is called a fractionating column. So electrical heater is giving the heat. Round bottom flask contains the solution. This time the solution belongs to two liquid solutions. In my case, I have taken water and ethanol. Water which has a boiling point of 100 degrees Celsius and ethanol which has a boiling point of 78 degrees Celsius. there is a fractionating column at the top of the round bottom flask. So this thing this cylindrical thing that you see is a fractionating column. I'm writing the boiling points on the top right. Water has a boiling point of 100 degrees Celsius and ethanol has a boiling point of 78 degrees Celsius. When the heat is provided, the ethanol and water both are going to vaporize. They're both going to turn into vapors. That's where the fractionating column comes in. The cylinder on the top of the round bottom flask is fractionating column. It has small glass beads filled in it. The glass beads are going to provide a high surface area where the vapors which have a higher boiling point, they condense back and they become the liquid again and they fall again in the flask. So ethanol and water, they're both going to vaporize, they're both going to rise their vapors, but only the vapors of the ethanol are allowed to pass through. So ethanol vapors will keep on rising, but water will condense back and water will fall down. That's why fractionating column helps in the separation based on boiling point. When the ethanol vapors rise, the thermometer will tell the reading of the boiling point of ethanol. So you will see 78 on the thermometer. The ethanol vapors pass through the Liebig condenser. Again, there is cold water being passed from the inside of the Liebig condenser, and this cold water will help in the condensation of the ethanol vapors. So throughout the Liebig condenser, the condensation happens, the ethanol vapors become liquid ethanol, and they are being collected in the conical flask at the end of the Liebig condenser. Water remains in the round bottom flask because the fractionating column separated the fractions, the vapors on the basis of the boiling point. Imagine I have a graph where the time is taken on the x-axis and the temperature is taken on the y-axis in the units of centigrade. So here we are concerned with how the temperature changes on the thermometer. You can see the thermometer at the top of the fractionating column. It's not touching the fractionating column, it's on top of it, so only the vapors touch it. Initially the temperature was lower, then it increases and then it becomes constant. A similar pattern is repeated again. Now what's happening? The temperature in the beginning was just 25 degrees Celsius because that's the room temperature. The temperature starts rising only when the heating begins. So you can see the first rise where the heating began. So temperature starts increasing only when the heating began. Then it becomes constant at exactly 78 degrees Celsius. It remains constant for a while. Why is it remaining constant? It remains constant for the amount of time, for the length of time when the ethanol vapors are evaporating. Sorry, they are vaporizing. We should not use the word of evaporate. Let's use vaporize. So ethanol is vaporizing right now. Water is condensed back. Only when all the ethanol has vaporized, only then the temperature will rise again. Because when the ethanol is vaporizing, it is boiling, only ethanol is allowed to pass through while the water condenses back. After ethanol is separated, the temperature rises again, and this time the temperature starts rising from 79, 80, 81, and then it becomes constant at 100 degrees Celsius. So the temperature remains at 100 degree for a while when the water is vaporizing, when the water is boiling. So this time the water is being boiled, water is vaporizing, and water is being collected. So you need to change the conical flask to collect water. The temperature remains constant when one of the component is vaporizing, then it increases, and then it becomes constant again when the other component is vaporizing. So you can confirm the identity of the vapors and then obviously what is collected using the thermometer reading. 78 degree indicates that only ethanol is vaporizing. 100 degree on the thermometer indicates that only water is vaporizing. And then when the temperature changes, it means that the vaporization and the collection is done and now the other component is coming. So you really quickly change the conical flask, and after 79 or 80 degree you change the conical flask because you know that now water will be coming in. So this is how fractional distillation works. I hope it's clear to you guys. I'd really love your feedback, guys. Thank you.